Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. In today's lecture, we will discuss Bezout lemma. This is actually theorem 2.3 in David M. Burton book. This theorem can be stated as if we have two integers a and b, not both of which are 0, then there exist integers x and y such that the GCD of a and b can be expressed as ax plus by. What does this form says? Ax plus by, actually this is the linear combination of a and b. This is the linear combination of a and b. So in simple words, you can say that the Bezout lemma says the GCD of any two integers a and b which are not both 0 at the same time can be expressed as the linear combination, and the GCD is the least element that can be expressed as the linear combination of a and b. So we before going to start proof, we take a simple example. Let a is 18 and b is 12. Then the linear combination of a and b is 18x plus 12y simply. I have made this table for the different values of x and y, and at these different values of x and y, I am calculating the value of linear combination 18x plus 12y. Suppose when x is 0, y is 0, then 18 into 0 plus 12 into 0, this is 0. When x is 0, y is 1, 18x plus 12y is equal to 12. When you put x is equal to 1, y is equal to 0, your answer is 18. When x is 0, y is minus 1, your answer is minus 12. Similarly, you can see other values. So these values 0, 12, 18, minus 12, minus 18, 6, 42, 12, etc. These are the values of the linear combination at different values of x and y. Further, if you find the GCD of 18 and 12 here, this is 6. 6 is the greatest common divisor of 18 and 12. Now, these are the key points that we will use in the proof. For these linear combination, we can observe that the linear combination of 18 and 12 could be 0, negative, positive. This shows that the set of linear combination of 18 and 12 is non-empty. This is the first thing. The linear combination of these integers, set of linear combination is non-empty. The least positive integer, linear combination of 18 and 12 is 6. This is also very important point. If you see the different linear combination, among all these linear combination, the smallest positive linear combination is 6. This is 6, the smallest linear positive combination. All other linear combination, although there are other linear combination that are also positive, like as 42, 12, 18, again 12, these are all positive linear combination, but 6 is the smallest one among all these positive linear combination. The linear combination that is smaller than this 6, this is 0, but this is not, this is neither positive nor negative. So the smallest linear positive combination is 6, that can be expressed as 18 into 1 plus 12 into minus 1 is equal to 6. You can find many other values of x and y for which this equation 18x plus 12y gives us 6. So the least positive linear combination of 18 and 12 is 6, which is the GCD of 12 and 18. This is very interesting. The smallest linear combination of 18 and 12 is equal to 6, but this 6 is represent actually GCD of 12 and 18. So from this example, you can see the proof. What we have to prove? We have to prove the same thing, that the GCD is the smallest smallest positive number that can be expressed as the linear combination of a and b here. So from this example, you can verify this. Further, is it possible that 1, 5, 15 are also in the linear combination of 12 and 18? The simple answer is no. This is not possible that when you find the linear combination of 12 and 18 and you find the answer of 12x 18x plus 12y is equal to 1, this is not possible. Equal to 5, this is also not possible. Equal to 15, this is also not possible. Why? Actually, we can see that all the linear combination of 12 and 16 are just multiple of 6, which is the GCD. If you again see the table, you can observe that all of these numbers 0, 12, 18, minus 12, minus 18, 6, 40 to 12, these are all actually the multiples of 6. So any of the number in this row is does not exist, which is not a multiple of 6. So this is not possible that in the linear combination, in the list of linear combination, 1, 5 or 15 will exist. The smallest linear combination that is neither positive nor negative, this is 0. And clearly this linear combination is smaller than least positive linear combination of this. Now we are in the form to prove this, to prove the theorem. So firstly, we will show the existence of this form, that GCD of integer a and b is equal to ax plus by. Firstly, we show the existence of this form. Then we will show the GCD is the smallest one that can be expressed as ax plus by. So we will prove this theorem in two steps. Firstly, we show the existence of this form, and then we will show that the GCD is the smallest one. So firstly, we consider the set S of all positive linear combination of A and B. This is the set S, that is the set of all linear combination of A and B. This is AU plus BV, where AU plus BV is greater than 0. Why we are taking here positive linear combination? Why we are not considering here negative linear combination? Because this is actually the definition of GCD. GCD is always the positive integers, and we have to show that GCD is the linear combination of A and B. So that's why we are not considering the case of negative here. Notice first S is non-empty. I have shown this by above example. The set of R linear combination was non-empty. But in the proof you can see here, for example, if a is any non-zero integer, then you can write it as a absolute is equal to a times u plus b into b into 0 by setting v is equal to 0. For example, a is any integer, either it is negative or positive. You can write it as a into u plus b and set the value v is 0, where u and v are the integer. So set this integer v is equal to 0. This becomes a absolute is equal to a times u. Now it depends on either a is positive or negative. If a is positive, then its absolute value will be positive. So a is equal to a times u. So this equation hold when u is equal to 1. If a absolute a is negative, then its absolute value will be negative a. Now this equation will hold when u is minus 1. So we can choose u is equal to 1 or u is equal to minus 1 according as a is positive or negative. So this shows this set S is a set of positive integer, and this is also non-empty. So these two things guarantees that we can use well ordering principle. What is well ordering principle? The well ordering principle says that every set of positive integer, every non-empty set of positive integer have a least or smallest element. So by the virtue of well ordering principle, S must contain a smallest element D. Suppose the smallest element is D. Thus, from the definition of S, there exists an integer x and y. Now, as D is the smallest element of S, and S is the set of all positive linear combination, so I can express D as the linear combination of AX plus BY. So we can write D as AX plus BY form. Next, our target is to show that D is actually nothing. This is equal to GCD of AB. So we will use the division algorithm for the first integer a, the division algorithm says that when you divide a by any positive integer d, there exists a unique integer q such that this is equal to dq uh, have the remainder r. So I can write a is equal to dqd plus r, this form where your remainder r lies between 0 and d. Now if we find the value of r from here, we can write r is equal to a minus qd. Substituting the value of d, as d is ax plus by, so we can write a minus q into ax plus by. Rearranging the terms, we have 1 minus qx into a plus minus qy into b. This shows also r is a linear combination of a and b. This is also the linear combination form of a and b, because q and x both are integer, so the difference of two integer is again an integer, so this is an integer, this is also an integer, so this is the linear combination form of a and b. So r is also a linear combination of a and b. It means this r is also element of S. Now we will compare either r could be greater than d or not, but r is less than d, because r is the remainder, and by definition of remainder, r should be less than d. Now when r is less than d, so what is the possibility for r? There is only one possibility for r, that r must be 0. This is the important point. Why does r is 0 here? You can see that uh, in this linear combination 6 that was the GCD of 18 and 12, and this is the smallest one smallest one, that is a positive, and that can be expressed as the linear combination of 18 and 12. Now all other linear combination are greater than this number 6. Now the number that is also linear, that can also be written as the linear combination of 18, 12, and which is smaller than 6, this is 0. So the only possibility, because d is the, because we have claimed that uh, d is the smallest element. Next we show that d can be written as the linear combination of ax plus by. So if you now write any element as the linear combination of a and b, it would not be a greater than d, because it would not be a less than d, because there is the only one possibility that for a linear combination that will be less than the linear combination of d. It is one possibility that it should be 0. Mean to say, you can write 0 is equal to 0x plus 0y. This is the smallest one, that would be less than this linear combination ax plus by form. So that's why here r is equal to 0. Again, I am again repeating here. From this example, you can observe that there are several linear combination which are positive, negative, and also 0. The smallest positive linear combination is 6, that is actually the GCD of 18 and 12. Now the linear combination that is also less than 6, this is 0, that is 0 is equal to 0x plus 0y. So this is the unique linear combination that is less than 6, but this is 0. This is not positive linear combination. This is neither positive nor negative. So that's why there is only possibility for r that we have written as a linear combination, it should be 0. Thus when you put here r is equal to 0 here, this becomes a is equal to qd. We have a is equal to qd. What does this represent? This represents the definition of divisibility, This shows D divides A. Similarly, we can prove that D also divide B. How? When you write B as when you apply Divine algorithm for B, now you will write B is equal to Q times D plus R, and by applying the same arguments, same steps here, we can prove that D divides B. Therefore, D is a common divisor of A and B both. Next, now if C is any arbitrarily positive common divisor of integer A and B, then C divides their linear combination of A and B. That is, C divides AX plus BY implies C divide D. I can verify these lines by again by a simple example. You can see that 3 is also 3 also divide 18 and 12 both. This implies 3 will divide any linear combination of 18 and 12. For example, the last row represents the linear combination of 18 and 12. You can see that each of the number is divisible by 3. 12 is divisible by 3, 18 is divisible by 3, minus 12 is divisible by 3. Every number is divisible by 3. So any number which divide 18 and 6, 18 and 12, it will also divide the linear combination of 18 and 12. Now the linear combination of 18 and 12 is actually equal to 6. That is the GCD. This implies the 3 also divides 6. So from this example, you can verify that 3 will divide GCD of 18 and 12. So now if C is any arbitrarily positive common divisor of A and B, then C divides linear combination, that is C divides AX plus BY, but AX plus BY is equal to D. So this implies C divide D. Next, by using the property that says that, and this property we have proven in our last lecture, if C divides D, then the absolute value of C is always less than or equal to absolute value of D. So D is greater than every positive common divisor of A and B, and that fulfills the definition of GCD. Hence, D is equal to GCD of B. What is the definition of GCD? The definition of GCD says that if A and B are integers, not both of them are 0 at the same time, a positive integer D is called GCD of A and B if D divides A, D divides B. If there exists another common divisor C, then C must divide D, and C is less than or equal to D. Then D is called the GCD. So we can see here the same conditions. C is a common divisor that divides D. C is less than D, so that D is a greater than every positive common divisor of A and B. So both of the condition of GCD are satisfied. Hence, D is the GCD of A and B. That can be written as a linear combination of A and B. So I hope now you have a clear understanding of Bezout lemma. So if you have any question or query, you can comment me or message me. Inshallah, I will reply you. So see you in the next lecture. Take care. Allah Hafiz.